Hi everybody, welcome to the 6.7. These are going to be the 6.7a notes. These notes are about the fundamental theorem of calculus and definite integrals, and we've already talked about the fundamental theorem of calculus. I'm going to put over here on the right what we've learned. There's kind of two conditions to the fundamental theorem of calculus. So the first part that we learned is that if you take the derivative of an integral with respect to x, essentially, you're just going to get f of x. So you're going to get the function that was inside the integral with this upper bound plugged in. So that was the first part of the fundamental theorem of calculus. We basically learned that the derivative and the integral cancel each other out. But today we're going to learn the second part of the fundamental theorem of calculus. And what this involves is actually evaluating the integral. So not taking the derivative of the integral, but figuring out what is the value of the integral. And so what we're really doing when we do that is we're figuring out what's the area under the curve. And so what this says right here is that the integral of a derivative is the original function from b to a, which means that this equals f of b minus f of a. So if you're taking the integral, you're basically going back to its original function. So if you're taking the integral of a derivative, you're going back to the original function, or you're going back to the function basically before that function. And so we're going from the derivative back to the integral. And then if you have these bounds, back to the original. If you have these bounds, you're actually evaluating. You're going to take the original with b plugged in, and you're going to subtract the original with a plugged in. Here is like a more formal definition of this. It says if f of x is continuous on the closed interval a, which is less than or equal to x, and is less than or equal to b, and g of x is an antiderivative of f of x. So what that means, remember, antiderivative is another word for integral, but an antiderivative is original function of a derivative function. It's like the original version of it. So if that's occurring, then the integral of f of x from a to b is going to equal that antiderivative from b to a. And then if you actually go to evaluate it, you'd have to plug in b and you'd have to plug in a. So another word for the word integral is antiderivative. So if you ever hear the word antiderivative, think integral. That's what that means. It's the opposite of the derivative. It takes you back to the original function. So there are going to be some and we've talked about antiderivative a little bit, and there are going to be some official rules that we'll memorize, just like how we memorize the derivative rules. But for today, we're just going to kind of try to logic our way through them. And so, reminder, an antiderivative is anything that kind of gets you back to the original function. So for example, the antiderivative of x squared, we're breaking this down a little bit. Okay, so the derivative of x squared would be 2x. The derivative of x squared plus 3 would also be 2x. The derivative of x squared plus pi would also be 2x. And then the derivative of any x squared plus a constant, which we're going to use c, is also 2x. And so if you ask, okay, what is the antiderivative of 2x? Well, any of these original functions back over here apply, right? An antiderivative is anything you could take the derivative of and you would get your given function. And so when we're thinking of the antiderivative of 2x, we're just going to think x squared plus c, because we don't always know what c is. And so that's going to help us evaluate this first function right here, okay? And so if I go to evaluate and I'm trying to find the antiderivative of x squared, it's going to be the function kind of above x squared. So I'm thinking, what am I taking the derivative of that would get me back to x squared? So one thing you might remember about the derivative is the power rule. And so the derivative of x squared, for example, is 2x. The derivative of x to the fourth power is 3x cubed. So every single time we take a derivative, we tend to lose a power. And so if I want to find the antiderivative of x squared, I'm going to write x cubed, because I know that the derivative of x cubed would leave this as x squared. But if I took the derivative of this as it is right now, I would get 3x squared. And we are trying to think of what function, if we take the derivative of, would get us x squared. So as it is right now, it won't work, but say really the only difference between this function and this function is that there's a 3 out in front. And so if I multiply by 1/3, then the antiderivative, or the derivative of 1/3 x cubed would be 1/3 times 3 times x squared. Because you remember, just drop down this cube, and then these cancel out, so you just get x squared. So the antiderivative of x squared is 1/3 x cubed, and then we're going to add a c, because any constant that we have there would get, like any constant that we have, once we take the derivative of it, would cancel out. And then because we are trying to find the area under the curve from 4 to 1, I'm going to add these little bounds right here, and then I'm going to evaluate. So when I go to evaluate, I'm going to do 1/3 4 cubed plus c, and then I'll have 1/3 times 1 cubed plus c. Now, one thing we're going to learn is there's two types of integrals. There's called definite integrals and indefinite integrals. And definite integrals are the integrals where you have bounds to them. And so when you have definite integrals, you're not always going to actually have to write the c down, because when I go to do this subtraction, these two c values will automatically cancel out. So I'm going to write them down for right now, just so you can kind of get the hang of it, but know that the c values will cancel out. So now I'm just going to evaluate this. 4 cubed is 64. So then I'd be doing 1/3 times 64. So I'd have 64 over 3 plus c. And then I'm going to subtract this whole situation over here. So I'd have minus 1/3, because 1 cubed is 1. 1/3 times 1. And then I'd have a minus c. And so this is what I'm going to talk about. I'm going to combine my like terms. So these will combine, and then these will combine. But just a reminder, these, adding their sign, the c's will cancel out always, because they're just the same thing. And so that ends up giving me 63 over 3, which equals 21. And so the antiderivative helped us figure out the area under the curve. The area under the curve is 21. So we're going to keep going. And again, like I said, there are rules. There's rules to do these quicker, but just so that we can kind of develop some skills, we're going to keep thinking about it in our head. So this next one, 6x squared, I know that I need a power, so I'm going to kind of do each piece separately. So I know for this one, I need a power 1 greater than x squared to get it down to x cubed, or 1 greater than x squared, so that when we take the derivative, it's x squared. So I know that the derivative is going to be x cubed. And then I need to think, okay, well, I'm going to pull this 3 down and multiply by whatever is here. So what number do I need to put there that would give us 6? And the answer to that would be 2. So the antiderivative of 6x squared is 2x cubed. Next, I need the antiderivative of negative 5x. So it's going to be negative, and then it's going to be squared. So then what needs to be here so that when I multiply by 2, I have 5 left, because I need to get this to be 5, and that would be 5/2. And then finally, the antiderivative of 2, well, what would I have to take the derivative of that would get me 2? It would be 2x. And if you are unsure whether our answer is correct, over here on the side, I'm just going to take the derivative of this right here. So the derivative of 2x cubed I know is x squared. The derivative of negative 5/2 x squared is negative 5x, and then plus 2. And that is what I had under the integral sign. So I figured it out correctly. But I want to know the area under the curve. I want to actually evaluate and figure out what number this is, not just like a function that represents the antiderivative. I want to use the antiderivative to help me find the area under the curve. So I need to evaluate this from 1 to negative 3. So just going to plug that into the function. I'll have 2 times 1 cubed minus 5/2 1 squared plus 2 times 1. I didn't even add the c here, because I could add the c, but because I'm evaluating this, I know that the c's are going to cancel out because of the rule, because I'm always going to subtract them. So that's why I didn't write the c in for this one, because it was just kind of a waste of space. So again, just plugging things in here. And now I'm kind of done with my calculus. After I do this, I'm just going to now evaluate. So I'll get 2 minus, I'm going to convert this into a fraction, 2.5 plus 2 minus 2 times negative 27, so that'd be negative 54 This would be 9. 9 times 5 is 45. So 45 over 2, which is 22.5. Then minus 6. This ends up giving me, 1.5. And then this gives me, negative 82.5. Now I'll evaluate that. These will turn into addition signs and I'll get 84. So the area under this curve from -3 to 1 is 84. And this is an exact area. Like, we're not estimating anymore. When we do this the algebraic way, we are figuring out exactly what it is. And so this algebraic way is replacing our Riemann sums, which is probably good news for a lot of us because Riemann sums can be kind of tricky, and also they're just not 100% accurate. They are just estimates. So we're going to do one more like this. Actually, I guess I have 2 more. No, I have 3 more. Sorry, we're going to keep going for a while. And then we're going to do some with calculators as well. So we're going to just keep moving. Feel free to pause at any point. So example 2 here, e to the x. Well, the derivative of e to the x is e to the x. So the antiderivative of e to the x, if we're moving the other way, is also going to be e to the x. So it'll be e to the x, and then we're evaluating from 4 to 0. So that just equals e to the 4th power minus e to the 0 power, which anything to the 0 power equals 1. So that's the answer for this one. So the area under the curve. And I don't need to, e to the 4th power is an exact answer, so there's no need for me to put that in the calculator and figure out what that value is. It would be better for you to keep your answer exact. Okay, moving on to our next one. Okay, now we have cosine of x. So what do we take the derivative of that would get us to cosine of x? And the answer to that is sine of x, because the derivative of sine of x is cosine of x. There's no sign change or anything because the derivative of sine of x is a positive cosine of x. If we were going the other way, there'd be some negatives involved. So I want to find sine of x from pi over 2 to 0. So I'm going to evaluate that. We're not using a calculator here, so you might have to pull up your unit circle. So just remember a unit circle. This is 0, this is pi over 2, this is pi, and this is 3 pi over 2. So we first need to find sine of pi over 2. Cosine is the x value in the unit circle, and sine is the y value. So if I'm trying to find sine of pi over 2, I need to think about what is the y value right here. And it's a unit circle, so the y value on these 4 quadrants, since it's a perfect, or it's a right angle, it's all 1. So sine of pi over 2 is 1, and then sine of 0, well, the y value here is 0, so it'd be 1 minus 0. So the area under the curve of cosine of x from 0 to pi over 2 is 1. Okay, one more before we get to some calculator problems. So before I even go to evaluate, we don't normally keep things in the radical when we do derivatives, right? We normally convert it into exponential form, and then we would take the derivative of. So while I work backwards as well, I'm going to do the same thing just to make it consistent with the way that we've seen it. So I'm switching that. This one's going to be the trickiest one probably. Now I need to think, okay, what do I need to take the derivative of that will get me here? And like I said, this is going to be trickier, but every time we do the derivative, we use the power rule and we lose an exponent. So if we're going the other way, we're going to gain an exponent. So this is going to be y equals 3/2, okay? Now I need to think of what will be right here. And one way I can do this is I can just I'm gonna do it over here. If you can't figure it out right off the top of your head, I'm thinking what, so the word what is an x. I'm thinking what times 3/2 would have to equal 2. So I'm just gonna solve this equation. So if I do this, if I want to get rid of 3/2, I would multiply 2 on both sides. I'd get x times 3 equals 4. And I have to divide 3, and I get x equals 4/3. So I figured out that this is 4/3. And then the antiderivative of 1 would be 1x. Or we're using y's in this situation because this says dy, so 1y. And then I'm evaluating from 4 to 0. So if I took the derivative of this, just to like continue to reiterate this, I would get this answer right here. So whatever's coming over here is the antiderivative of this. It's the opposite. So now I'll have 4/3 y to the 3/2 power. Wait, I'm not actually plugging anything in. Sorry, I'm plugging in 4 3/2 plus 4, because I plugged that in for y, minus, well, this part's going to be kind of nice because it's just all going to cancel. So all of that's going to cancel in a second. Oh, this is annoying, but we're still going to do it. So this is going to be 4/3. The way I rewrite this, if I'm not using a calculator, which we're trying not to do right here, is it's like you're taking the square root. You look at the bottom, the denominator of your exponent, and you put that on the outside, and then you put this part on the inside, essentially. All of this is going to equal 0, because 0 to 3/2 power is 0, and then plus 0 would be 0. So that's going away. This is going to equal the square root of 4 cubed is 4 times 4, which is 16, times 4, which is 64. And then the square root of 64 is 8. And we're adding 4. We're going to keep going, so this is going to equal 32 over 3. I need to change 4 to a fraction with a denominator of 3 if I want to be able to add those. That will be 12/3, and so then what I get for the area under the curve is 44/3. That was a lot of algebra that I'm sure we really loved doing. So pause if you need some time to process that, but we're going to do one more problem, and this problem will be so much easier because I'm going to teach you how to use this to do this on your calculator. As you guys are learning this, like, feel free to check your work using the calculator, and then on a test or on the AP test when you have a calculator, like a calculator active problem and it's asking for the integral, like, don't take your time and solve it by hand. Like, if you have a calculator on the AP test, use the calculator. A lot of times they're trying to test, like, if you understand the meaning of the integral or if you can use the integral. They're not actually testing if you can find the antiderivative. And so, like, don't waste your time. So what you're going to do on the calculator, I'm going to walk you through some steps, is the way that you evaluate this is very similar to the way that you evaluate derivatives. Like, it's the kind of the same process, except for instead of pressing number 8, you press number 9. So you're first going to press math on your calculator, and see if I can pull this up. See if I still have the Calculate 84. That's the news app. Oh my gosh. Okay. Calculate 84. So I might have to watch an ad. Be prepared. Okay, never mind. I can't show you this. It will take too long. So hopefully you can follow along with this and I can help you in class. But press the math button on your calculator. And then your next step is you're going to press, well, you can either scroll down to 9 or you can just press number 9. And when you get that, you should see, it'll say like FINT, like that's what it'll say, which means function integral. And then it'll say like this, and then you're going to press enter. And it's going to pop up, and it's going to have like a bunch of blanks. So you'll see the integral, you'll see the bounds, you'll see a blank right here, you'll see a blank here, and you're going to fill these in. So you're going to fill it in exactly how you would think. You're going to put 0, 1, you're going to put the function in here to the 5th power, and then you're going to write dx right here. And then you will press enter after that, and you will get 600. You should get 651 out if you did that correctly. And if this was like not easy enough to understand, I can do it again in class tomorrow. But you should get 651 out of that. And so that's just like a really quick way to do this. And then if you do the next one, I'll let you guys try that on your own. But if you do it correctly, you should get 0 out. So we're just using the calculator to help us do these problems a little quicker, because maybe we're trying to use the integral to answer a different kind of question is normally what happens. Okay, last question. This is a challenge question. So evaluate the definite integral. Okay, so we have this function that we want to find the definite integral of from -4 to 0. But the function is a piecewise function. And so it's defined by different pieces for different bounds. So it's defined by 4x cubed plus 2 when the x values are greater than -1, and it's defined by 3x plus 1 when the x values are less than -1. So how we're going to do this problem, it's a challenge. So feel free to try it by yourself, but we are going to break this integral into two pieces using our integral rules that we learned the other day. So if we're going from -4 to 0, well, from -4 to -1, it is defined by this function because this is the one that's used when x is less than -4. So I'm going to rewrite this integral. Overall, I have to go from -4 to 0, but I can split the integral into two pieces. So I'm going to go -4 to -1. And from -4 to -1, f of x is equivalent to 3x plus 1 dx. And then when x is greater than -1, and we only have to go up to 0 here, it's defined by 4x cubed plus 2 dx. And for this one, for the sake of time, I want you to use your calculator for this one. So this is an example of a test that the question you might see on the AP test, where they're trying to figure out if you know to split the integral. They don't really care if you know how to find the integral. They're testing to know if you understand like the properties of integrals. So if you use your calculator to evaluate these, you should get -19.5 plus 1, and your answer will be -18.5, and that is the answer. And then you are done with the notes. So write down any questions. Feel free to send me an email. Best of luck.